In this video, I introduced the one-side limit, and so armed, I then show you how to find the limit of the 6 major trigonometric functions and follow that up with a limit of a very important expression containing a trig function. So a one-side limit is so similar to the normal limit, that's probably best just to dive right into the definition. One major difference is that the notation is not x is approaching c, but rather x is approaching c with a plus in the upper right hand corner. That means from the right. That means in the limit, we only consider x values that are not just near c, but those that are greater than c. In a left-hand limit, we would put a minus in the upper right-hand corner above the x value that we're approaching, and we only consider x values that are less than it. So in a general sense, if you have a bunch of x values you're considering, and you have a limit value that you think the function approaches, if that really is the limit value, you can say that I want to force the function to be this close to the limit value of L. Well, if that's true, then I should be able to restrict my input around c, but greater than c, so that for all those x values, the corresponding function value is in the desired restriction range for the output around and near the limit value of L. We can investigate these limits numerically, graphically, or analytically, whether x is approaching a number or from the left to the right. For example, if I said, look at this particular table, notice how the x values are approaching 2 from the right, and how the corresponding outputs appear to be approaching 4. So I would then guess that the limit of this function as x approaches 2 from the right would then be 4. You can also investigate the limits graphically. For example, if I say let x approach 3 from the right, I would then graphically draw my line, and then I would take a x value that is greater than that x value, in this case greater than 3. I would draw that point, and then I would allow the point to move towards the vertical line. As it does so, you should notice that it approaches a point in the plane. The coordinates of that point are 3, 0. So I would guess then that the limit of this function as x approaches 3 from the right would be 0. But at the same time, you should notice that I could also do the limit from the left, and the difference is that the limit this time would be 2 instead. Notice that the limits are different. Let's try one quick example or two. I want to know the limit of this function as x approaches 1 from the left, as it approaches 1 from the right, if just x approaches 1, and then what's the function value at 1? And finally, is the function value at 1 the same as the limit as x approaches 1? Are these two things equal? So if x is approaching 1 from the left, that means I'm following this path right here, going towards that point in the plane. I don't care if it's a point in the graph or not, it's a point in the plane. The coordinates of that point are 1, 1. So then I'm approaching the value of 1. If I take the path going towards 1 from the right, that would then mean that I'm approaching a point in the plane again. This time the coordinates are 1, 0. So the limit is 0. But if you're coming from the left or the right, it doesn't matter. The full limit doesn't exist. You don't come towards one single value as x approaches 1 in general. So that limit just does not exist. But the function value at 1 does exist because there is a filled-in point on the graph when x is 1. That y-coordinate is 1. So the limit of the function as x approaches 1 does not equal the function value at 1 because one of the sides doesn't even exist. Let's try that again. I'll erase this. This time, let's go find the limit of the function as x approaches 2 from the left, 2 from the right, just 2 in general, and let's find the function value 2. And again, ask the question, is the limit of the function as x approaches 2 the same as the function value at 2? So, if I'm allowing x to approach 2 from the left, I'm following this path going this way, and notice I'm approaching a point in the plane. The coordinates of that point are 2, -1. So the y value is -1. That's the limit value. If you approach from the right, notice that you're approaching a point in the plane, and the y coordinate of that point is -1. And if you remember, here's the dotted line. See how I'm going to the same place? So you remember from previous videos that means the limit here is that y coordinate of that point. That limit is 1. Notice that the limit from the left and the right were both equal, and because of that, the entire limit had to also exist and be that value. But the function value of 2, though, is 2. It's because of that filled in point way up at top. So the limit of the function as x approaches 2 does not equal the function value at 2, even though this time they're both real numbers. Now I could go over the other examples, but I will save that for class time instead. So you might have noticed that if the left-hand limit and the right-hand limit came to the same point, well, that would have to mean then the whole limit exists, and it's that number. If the whole limit existed, well, then you have to come to one point on the graph. That means the left and the right limit had to exist and are the same number. So we use that as a new limit law. If you ever want to know if the limit of a function exists as x approaches a number, you can instead approach that limit from the left and the right separately, show those limits exist and happen to equal the same thing. Then the entire limit must also exist and be that number. This is really useful for piecewise functions because oftentimes functions that are defined piecewise change definition to the left and to the right of a single value. If you want to find the limit of a function from one side or the other, all the limit laws actually still apply. The reason is because all you're doing is restricting the x values even further. So, for example, to find the limit of this polynomial, you already know how to find the limit in general. So here, you just plug in the number, because the limit of a polynomial is found just by straight up evaluation. And that's because there's no conditions on the sum, difference, or constant multiple rules, or the product rule for that matter. Here, though, the limit of a quotient, you remember there is a limitation. You cannot let the denominator be 0. If it is, then you can't use that limit law. Here, if you just plug in 2, doesn't matter left or right, notice that, well, you get a 0 in the denominator, but you still have that 0 over 0 form. So you can still use the limit laws as you did before. You would just take the limit as x approaches 2 from the left and factor the numerator and factor the denominator. In this case, you don't have to. You would then cancel common factors using the replacement theorem. So the limits are the same because we're talking about the exact same function values for the range of x values we're interested in. And now we have a limit of a polynomial. So we just plug in the number, and the answer is 4. So the function gets as close as we like to 4 by just restricting x close enough to 2, but less than 2. So obviously what we need is an example where the limit from the left and the right is meaningful and different from just the full limit. So let's look at these. In each of these cases, you would like to be able to just plug in the number to get the answer of 0. But only one of them actually is 0. The others don't exist. The first one would be 0. Now, why? Because if you're using the limit as x approaches 2 from the right, one of the conditions for the square root was that the inside had to be always non-negative for the choice of x values you're allowed to use. If x is more than 2, this expression is always more than 0. It just gets close to 0. So that limit indeed would be 0. While here, though, this one just does not exist. And this one also just does not exist. The reason the limit from the left doesn't exist is this expression, if x is near 2 but less than 2, that would mean then when you square it, it'd be near 4 but less than 4. And if you subtract 4, well, that means that the x squared minus 4 for the range of values I'm talking about is negative. You can't take the square root of negative numbers. There are no function values to approach anything. So that limit just doesn't exist. Once one of the cited limits doesn't exist, then automatically, by the new limit law I just gave you, the whole limit doesn't either. Now, the left and right hand limits, together with the replacement theorem, are often needed for limits of piecewise defined functions, especially where the functions change at their domain breaks. So, for example, let's find the limit of this function as x approaches 2 from the right, from the left, just in general, and let's find the function value at 2. Now, in order to find the limit of this function as x approaches 2 from the right, that means I'm restricting myself to only those x values that are more than 2. Well, if x is more than 2, the function is just 2x plus 3. So I can replace the function notation with what it's equivalent to for the range of values I'm interested in, as we're talking about the same y values anyway. But the limit of that, it's just the limit of a polynomial. So I can just plug in 2 to get the answer of 7. To find the limit of the function as x approaches 2 from the left, that would mean that x is less than 2, but also that it's near 2. That would correspond to the interval values of 0 is less than x is less than 2. And in that interval, the function is the same as the value 1. So I can replace the function with what's equivalent to for the range of values I'm interested in. And that's the limit of a constant, so that's just 1. Unfortunately, the limit from the right and the left are different values, so the entire limit just fails to exist. Does not exist. But the function value at 2 does exist. That value is 2. So notice that the limit as x approaches 2 of the function doesn't exist, and yet the function value at 2 does. So those are different concepts. Let's try it again. I'll erase this. Alright, so this time, let's find the limit as x approaches 0 from the right, from the left, in general, and let's find the function value at 0. Well, if x is approaching 0 from the right, that means it's more than 0, but it's near 0. So that would be the interval from 0 to 2 again. And in that interval, the function is equivalent to the function 1. So I can replace the function notation with what it's equivalent to for the range of values I'm interested in. And that limit is just a constant, so that's just the constant 1. Next, to find the limit as x approaches 0 from the left, that would mean x is less than 0. That would have to be the interval from -1 to 0. And in that range, I'm taking the limit as x approaches 0 from the left, and I can replace the function with what's equivalent to. In this case, that's x plus 1. That's a polynomial, so to find the limit, just plug it in, and you get 1. Here, the limit from the left and the right are both the same number, so the entire limit must be 1. But look at the domain. You'll notice that x equals 0 is not mentioned. So f of 0 does not exist. Once again, the limit of the function as x approaches 0 is a number, and yet the function does not exist at 0. These are different concepts. Now, I could do other examples, but I think this is enough for now. I'll leave more for class time. When you're looking at limits of piecewise functions, you have to know when or when not to use limits from the left and the right. A good rule of thumb, though, is if you're trying to find a limit of the function at the domain break, especially if the function changes to the left and the right, you have to do limits from the left and the right. You have to write down the notation. So here, for this function, I want to know the limit as x approaches 3. Since the function changes definition from left and right, I have to first find, hey, what's the limit of this function as x approaches 3 from the right? That would then mean I have to take the limit as x approaches 3 from the right. If x is greater than 3, the function is equivalent to x cubed minus 2. That's the limit of a polynomial. You can just plug in 3 to get 3 cubed minus 2. That'd be 25. I also have to find the limit of this function as x approaches 3 from the left. And if it's approaching 3 from the left, that means x is less than 3. So the function in that case is equivalent in value to 8x plus 1. And that's a polynomial. Just plug in 3 and you get 25. Because of this work, you could then say, so the limit of this function as x approaches 3 is just 25, because the limit to the left and to the right are the same values. You have to show all that work in order to get full credit. One-side limits are also useful if you see absolute values, because an absolute value is actually a piecewise defined function. It is x if x is greater than or equal to 0, or it's negative x if x is less than 0. So to find this limit, I would say, well, if x is less than 0 and I want the absolute value of x. Well, the absolute value of x is the same as saying the opposite of x. Because if x is negative, then the opposite of that x is positive. By doing that, now notice that you have a common factor of x. You can then go and cancel those x's to get the opposite of x plus 3. And to find that limit, it's just a limit of a polynomial. You just plug in the number. So in this case, you get -3. And that's the right answer. Now you've seen two previous examples where the limit of the function was not the same as the function evaluation. Well, I want to show that for the trig functions that it's actually true. So we're going to do a simple version first and just state the statement in general. So I'm going to prove to you that the limit of the sine of theta as theta approaches 0 is the same as just the sine of 0. In this case here, the angles are all in radians. So I've already drawn a picture for you of an angle that is larger than 0 radians and less than pi/2. That would then have a point of intersection on the unit circle. We know that point on the unit circle would be the cosine of theta, comma the sine of theta. Now, please compare the following regions. Notice that the area of the triangle you see right there is obviously bigger than or equal to 0. But the area of that triangle is also less than the wedge that is created by the angle itself. Well, it winds up being that the area of the triangle is going to just be 1/2 the sine, because it's 1/2, the base is 1, and the height is the y-coordinate of that point, the sine of theta. So that's 1/2 sine of theta. And we maybe remember that the area of a sector is 1/2 theta times the radius squared. So here the radius is 1, so the area of that sector is 1/2 theta. And that's true then, based upon the picture, for any angle between 0 and pi/2 radians. So let's take that inequality and just double it to get rid of all the complications. And then notice that the limit of the left-hand side as theta approaches 0 from the right, and the limit of theta as theta approaches 0 from the right, in each case you're taking the limits of polynomials, the limit is 0. So by the squeeze theorem, the limit of the sine of theta as theta approaches 0 from the right is 0. Now graphically, think about it. That means if you graph the function, the sine of theta, that as you approach the line theta equals 0, you're going towards the origin because you're going towards the y value of 0 and the x value of 0 at the same time. But the sine function is odd, which means the graph is symmetric with respect to the origin. So then whatever happens to the right-hand side of the y-axis would also have to happen on the left-hand side. So if on the right-hand side you're going to 0, then on the left-hand side, as theta approaches 0 from the left, you also have to go to 0. So in each case, from the left or the right, the limit is 0. So by the limit law I just gave you today, that means the whole limit must be 0. And we notice that 0 is the same as the sine of 0. So that proves then the limit of the sine of theta as theta approaches 0 is the sine of 0. Now I could do some more tricky algebra and trigonometry and use some limit laws to prove lots of things about the trig functions, but I'd rather not prove them, instead just give you the results. So if you take the limit of the sine or the cosine as x approaches any number, it's the same as just function evaluation. You can just plug in the number. That's great. That means that we can find the limits of lots of trig functions just by plugging in the number. So by extension, since the tangent and cotangent and secant and cosecant are just divisions of sine and cosine with one or not, or just each other, you can find that the limit of all the other trig functions is the same as just plugging the number, provided that that number is in the domain. If it's not in the domain, then the limit just doesn't exist. So for example, if I wanted to find the limit of 2x times the sine of x, you could push the limit through all those pieces. Eventually you get the limit of x. You'd have the limit of the sine of x in each case as x approaches pi/3. In those two limits, you just plug in the number. So to find the limit of this function, you just plug in the number, a lot like a lot of the easier ones. So be careful here. You have to get nice answers, so you can't get decimals. Decimals just mean rounded. So you have to get the exact expression of the answer. That's why the answer has a square root in it, because at some point I had to take the sine of pi over 3, which was the square root of 3 over 2. It just canceled with the 2 that you had before. Now that previous proof was just a warm-up for this one. I need to show that the limit of the sine of theta over theta as theta approaches 0 is 1. We'll need that limit for later on in a very important computation. So I've once again drawn the unit circle. I've drawn the angle theta in standard position so that the terminal side intersects the unit circle. When it does so, the coordinates of that point are the cosine of theta, the sine of theta. I've labeled points P and Q and R, and also I have another point that I'll need later on. So notice that the area of this red triangle from PQR, that area is certainly less than the blue sector, just like we'd had before. But if you go from Q and draw a perpendicular line to the x-axis until it hits the terminal side of the angle, you would then get another triangle, and that area is larger than all the others. Well, looking at the picture then, for all angles from 0 to pi over 2, 1/2 the sine of theta, that's the area of the red triangle, remember, is less than or equal to 1/2 theta, that's the area of the sector, like I showed you before, and that's less than or equal to 1/2 the tangent of theta. And that's because that's actually the area of the black triangle. Well, but take that inequality now and double it. When you do so, you just get rid of all the fractions. Convert the tangent into sine over cosine. Now we don't have a tangent anymore. Then divide the entire compound inequality by the sine of theta. And since the sine of theta is positive for this range of x values or angles, you don't change the inequalities. So because of that, you then get this compound inequality. Now this is an increasing set of numbers that are all positive. If you take an increasing set of numbers that are all positive and take the reciprocals, the result is decreasing. So I'm going to take the reciprocal of all these things and then just change the directions of the inequalities. And I'll just write it from smallest to biggest. That gives you this set of inequalities. This is now still true for all angles from 0 to pi over 2. But notice the cosine of theta and the function 1. If you take their limit though, as theta approaches 0 from the right, each of those limits is 1. So therefore, by the squeeze theorem, the limit of the sine of theta over theta as theta approaches 0 from the right is 1. Lastly, the sine of theta over theta happens to be what we call an even function. If you graph it, it would be symmetrical about the y-axis. So if for the y-axis, when you come from the right of it, you go towards the y value of 1, and everything's mirrored on the other side, then the limit of the sine of theta over theta as theta approaches 0 from the left would also be 1. That means then the full limit as theta approaches 0 would have to be 1 also. And that's the result. Let's use this a few times. Now remember, the limit of the sine of u over u as u goes to 0 is 1. The u can stand for anything. As long as it's an expression that goes to 0, and you take the sine of that expression and you're dividing by that expression, the limit of that would then be 1. This is the last type of skill that we're going to really need to use later on in calculus, which is you need to be able to rewrite expressions to make certain things appear. There's often times where you simply have to rewrite the expression to complicate it just so that you can use certain rules. This is a great example of using that skill. So for example, I can't find what the limit of the sine of 3x over x is because I need to have a 3 in the denominator to use the rule I have. But that's easy to fix. I'll just complicate it instead of simplifying. I'll put terms in. I'll multiply the numerator by 3 and I'll multiply the denominator by 3. I'll just put them in different places. Now I can take the 3 out by the limit laws, and I recognize the limit of the sine of 3x over 3x. And if x is going to 0, then 3x goes to 0. That means this is 1. So the answer then is 3 times 1. It's 3. Let's do that again. I want to know the limit of the sine of 4x over 5x. So the limit of the sine of 4x over 5x. Again, I can't use the trick I have because I need the angle and the denominator to be the same. But I can fix that by just rewriting things. Just moving terms around, complicating the expression to make certain things appear. The 5 is in the way. I'll take that 5 out. So think of it as 1 over 5 for now. I have the sine of 4x still sitting here, and I have an x here. That used to be the 5x. I want that to be a 4x. That's easy. I'll just divide by 4 and multiply by 4. There we go. That then is the same as 4/5 times the limit as x approaches 0 of the sine of 4x over 4x. And notice the angle and the denominator are the same. And if x goes to 0, then of course 4x goes to 0. So this is 1. So the answer is 4/5 times 1, which is 4/5. Let's do it again. Now, you probably noticed in the two previous examples, see how the numbers came out? See, it was 3 and 4/5. Look at the original function. See the 4x and the 5x? So a lot of times students try crazy things to get answers. I've seen students say, hey, to find this limit of the sine of 4x over 5x, let's just get rid of the x's because they cancel, right? And I don't like sine, so the answer is 4/5. I would not accept that. That's just ridiculous. What I've done is acceptable work. You just writing down 4/5 at the end would not be. Just giving me the answer is not acceptable work. You have to support your answer. So for example, here, to find this limit, this is what I would do. I want the angle and the denominator to be the same. I'm not going to change the angle. So I'll write the limit as x approaches 0. I'll take the denominator, and I want it to be x squared. Well, I can't just square it, because you can't do that. I can only multiply and divide by the same thing. So I'll choose to multiply the denominator by another x. That will give me the x squared. And then multiply out front by x. Now I can use the limit laws. This time I would write that's the limit of x as x approaches 0 times the limit of the sine of x squared over x squared as x approaches 0. And this limit, because the angle and that denominator are the same, and when x goes to 0, x squared goes to 0, that limit's 1. But the first limit is 0. So now the answer is 0 times 1 is 0. And notice there wasn't a 0 in the first problem. So you can't just do some crazy canceling to get the answer always. You really need to use the algebra. Let's try some more difficult problems now. Sometimes you need to use identities, or you have to put in terms that are missing. So for example, here I don't have a division of the angles, but I can fix that. I can write this as the limit as x approaches 0. I'll complicate the expression, not simplify, by in the numerator and in the denominator, I choose to divide by x. I'm allowed to do that because x isn't 0, remember? There you go. And then in the numerator of the large fraction, I want the denominator of that fraction to be a 3. So I'll divide by 3 and multiply by 3. The same thing in the denominator of this large fraction. I want the x to be 2x. So I'll divide by x, divide by 2, and multiply by 2. I can then use limit laws. This will be 3/2. The constant just comes out. And then you'd have the limit of the sine of 3x over 3x as x approaches 0. And the sine of 2x over 2x as in the limit as x approaches 0. And each of those limits are the form we wanted. So that's 3/2 times 1 over 1. That's 3/2. This next limit, the tangent of 2x over x. Now I don't have a sine anymore. But I remember, though, that the tangent of an angle is the same as the sine of an angle over the cosine. I'll use that. So I will complicate the expression to make the things I want to appear. This is the same as writing, then, 1 over the cosine of 2x times the sine of 2x over x, because the sine of 2x over cosine 2x, that's the tangent. But then I want this x to be a 2x, so I'll divide by 2 and I'll multiply by 2. There you go, I'll put it there. This then equals the limit as x approaches 0 of 2 over the cosine of 2x times the limit of the sine of 2x over 2x as x approaches 0. The first one, just plug in 0, you would get 2 over the cosine of 0, which is 1. And this other limit, you recognize, is just times 1. So that's 2. The last one, this is then equal to. I will then write this as the limit as x approaches 0 of, think of it as 6, put the x here, and put the cotangent, take its reciprocal using the identities, and put it as a dividing by a tangent. You can then write this as 6 times the limit as x approaches 0 of x over the tangent of x. And without much work, you should be able to see that this is actually something of this form, because it's the sine of an angle divided by a cosine of an angle. That's the tangent. It's just reciprocated. That limit then actually is 1. So that's 6 times 1. So in the interest of space, I'll just cut the work a little short. And that answer would be 6. Last two problems. This time, I want to know the limit of 1 minus the cosine of x over x. This is another one of those actually fairly important limits that we're going to need later on. Unfortunately, though, there's no sine in it at all. So I need to fix that. So, like I've done before, I'll complicate things. I'll kind of like unsimplify. So somehow I want to get a sine out of it. Well, I remember, though, that 1 minus cosine squared is sine squared. So to get that, I'll take this numerator and this denominator, and I'll multiply by 1 plus the cosine of theta in the numerator and the denominator. That way in the numerator, it sets up a difference of squares. So this will become then the limit as x approaches 0 of, you would get 1 minus the cosine squared of x all over x times 1 plus the cosine of x. Don't distribute that product. That would then be the limit as x approaches 0 of, the numerator is just the sine squared of x, and that's all over x times 1 plus the cosine of x. Remember, I want to get the sine of x over x by itself, so I'll write that down right away. I have the limit as x approaches 0. I will get the sine of x over x times, this must be the rest of the fraction, so there's still a factor of the sine of x, and there's still 1 plus the cosine of x. But that, oh boy, long problem, right? That would then be, you can take the limit as x approaches 0 of the first factor in that product by the limit of the product rule, is a product of limits. And then you have the limit as x approaches 0 of the second factor in that product, the sine of x over 1 plus the cosine of x. The first limit's 1. The second limit can be found by just plugging in 0, because it's in the domain of the trig function. So then you would get the sine of 0, which is 0, over 1 plus the cosine of 0, which is 1. So this is 1 times 0. It's 0. That's the answer. Last one. To find this limit, notice that you can rewrite it kind of like I just did. Take the sine of x separately, and the denominator, there's a common factor of x. Take it out. What's left over is another fraction with a cosine and a 1 plus a cosine of x, because I factor that x out. Take the limit of that. So the limit of the product is the product of limits. That would then be the limit as x approaches 0 of the sine of x over x times the limit of the cosine of x over 1 plus the cosine of x as x approaches 0. The first limit is 1. The second one 0 is in the domain of the function. Just plug in 0. So the answer then would be the cosine of 0, which is 1 over 1 plus the cosine of 0, which is 1. And that would then give you 1 times a half. It's 1/2. That's the answer. And that gives you a basic understanding of one-side limits and how it connects to the overall limit, and then various trigonometric limits.